Hello everyone. Today we are going to start a super exciting topic in physics, and that is force. That is force. Now don't think of it as a heavy scientific word. Let look at screen. What do you see here? A boy trying to move an elephant. In the first picture, he is pushing the elephant from behind. In the second one, he is pulling it with a rope. So, in the simplest word possible, any push or pull on a body is called force. Whenever you open a door, you either push it or pull it, right? That's exactly what force is. But in physics, we define it a bit more professionally. Look at the definition below. Force is a physical quantity that changes or tend to change the state of rest, state of motion, or shape and size of an object. Now, let's break this down and understand what force can actually do in our daily lives. Look at these five amazing effects of force. First, move a stationary object. First, look at picture number 1. A football is just sitting on ground, it's rest, but the moment a player kick it, it start moving. What did the kick do? It applied a force that moved a stationary object. Second, change the direction of a moving object. Second, look the batsman. The bowler bowls the ball in one direction, but the batsman hit it and sent it toward the boundary in completely different direction. So force can change the direction of a moving object. Okay. Third, change the shape or size. Third image, you have a spring or rubber band, anything. If you pull it from both sides, what happened? Its size increases, its shape changes. So force can change the shape or size of an object. The fourth, stop a moving object. Look at the kid catching a ball. The ball was flying through the air, but the moment it hit his hand, it stopped. This means force can also stop a moving object. Now, fifth, change the speed of a moving object. And finally, look at these kids playing with tires. When they hit the moving tires with a stick, it start rolling even faster. By pushing it repeatedly, they are changing its. Let's move to the next slide. Now, how do we measure force? The SI unit of force is Newton, denoted by capital N. We denoted force with the symbol F. Always remember, force is a vector quantity. This means it has both magnitude, means value, and direction. Look at the screen. If we take the right side as positive, the force is F is equal to plus 10 N Newton. If the force is applied from the left side, the direction changes, so we write F is equal to minus 20 Newton. The minus sign simply show the opposite direction. Okay. Now let's understand net force or resultant force. It means the total force acting on an object. Look at the green box. Two equal forces of 200 Newton are pushing the block from opposite sides. Will the block move? No, because they cancel each other out. This is called balance force. Balanced forces. Here the net force is always zero. There is no change in the speed of direction of the object. The two forces are equal in value but opposite in direction. Now unbalanced force. Now look at the red box. What if the forces are not equal? One side applied 200 Newton and other applied 120 Newton. To find the net force, we subtract the smaller force from the bigger one. So net force is equal to 200 Newton minus 120 Newton is equal to 80 Newton. The block will move toward the right side. This is called unbalanced forces. Here the net force is not zero. It causes a change in speed, direction or both, just like kicking a football to make it fly. Okay, the forces are unequal and opposite. Clear enough? Balanced means no motion, unbalanced means motion. Let's move to the next slide. First, look at the unbalanced force slide. Net force is not zero here. One team pull with 10 Newton to the left and the other pulls with 6 Newton to right. The net force is 4 Newton to the left. Change in speed because the force are unequal. The rope and the kids will start moving faster toward the left. Changes in direction. It can easily change the direction of motion of the object. Has acceleration. Since there is a net force, the object will accelerate in that direction. Now, right slide balanced force. Now look at the balanced force slide. Net force is zero. Both people are pushing the car with an equal force of 20 Newton from opposite direction of each other. They completely cancel each other out. No change in speed. The car stays exactly where it is. Its speed doesn't change. No change in direction. The car will not change its direction of motion. Here zero acceleration. Since the net force is zero, the object has zero acceleration. Now we are entering one of the most important parts of this chapter, Newton's first law of motion. Let's read the official statement together. A body remains in a state of rest or of uniform motion in a straight line unless an external force is applied on it. This looks like a long sentence, but it simply means that objects are incredibly lazy. They just want to keep doing whatever they are already doing. It breaks down into two simple conditions. First, body at rest, left box. First, look at the left box on the left. We have a basketball sitting completely still on the surface of the moon. It is a body at rest. Will it move on tomorrow or next year? No. It will remain at rest forever unless an external force is applied, like someone's coming over and kicking it. Case number 2, body in motion right box. Second, look at the box on the right. Imagine you throw that same basketball in the deep space. It is a body in motion because there is no air or friction in space. The ball will never stop. It will keep moving with the same speed and in the same direction forever. It will only stop or change its path unless an external force is applied, like hitting an asteroid or entering a planet's gravity. In the previous slide, we saw that a ball in space keeps moving forever, but what happened in the real world? Look at the screen. If you roll a football on grass, it eventually slows down and stops. Why does this happen? If Newton's first law say a moving object should stay in motion forever, why do things stop on Earth? The hidden force friction. The answer is simple. In the real world, objects are not free from external force. There is a hidden enemy working against motion, and that hidden force is called friction. Now, Newton's first law is also as the law of inertia. But what exactly is inertia? Look at the definition at the top, the property of an object to oppose any change in its state of rest or of uniform motion. In simple terms, inertia is the laziness of an object. It is the natural tendency of any object to resist a change in its current state. If it's sitting still, it want to stay still. If it's moving, it want to keep moving. The relationship mass and inertia. But doesn't every object have the same amount of inertia? No. Look at the golden rule in the middle. More the mass, more is inertia. Inertia depends entirely on how heavy an object is. Let's compare the two examples on the screen. Case 1, less mass, less inertia. Less mass means less inertia. On the left, a boy is pushing a bicycle. A bicycle has less mass. Because it has less mass, it has less inertia, meaning it offers very little resistance to change. Therefore, it needs less force to start moving or to stop. Now case 2, more mass, it means more inertia. On the right, the same boy is trying to push a car. A car has a much more mass. Because it has more mass, it has more inertia, meaning it strongly resists any change. Therefore, it needs a lot more force to change its state of rest or motion. You cannot move a car as easily as a bicycle.